Yeah, okay.
Yeah,
I think
okay, I think
we can start. Yeah, I can see.
Oh, okay, good. So, good morning, everyone. So, I'm Anusree. I'm an AI engineer in a company called Innovation Incubator. So, today we'll be discussing on the applications of AI in the field of healthcare. So, and also we will also discuss what are the challenges that is faced by AI in healthcare and some of the anecdotes where the AI has failed due to some of the limitations that we still have. So I'll start presenting. Can you see the screen?
Yeah, Anushri, your screen is visible.
Okay, cool. So yeah, so as I said before, it's AI applications in healthcare. So, Deep Tech is a company which provide AI solutions, usually in the field of healthcare. And one of their products is called GenQ. So, it is actually used for population screening for diseases such as tuberculosis and COVID 19. Usually, like when GenQ was first introduced, it was just for tuberculosis, and it was with the advent of COVID 19 that they extended their platform to diagnose COVID 19. So, these diseases actually need very speedy screening. So, diseases don't spread fast, and also they need large scale screening. So that is because these kind of diseases, that is tuberculosis and COVID-19, actually is a very contagious, and it the main point in controlling this disease is the timely diagnosis of this and isolation of patients. So if this process is not done properly, even if we have medicines, when if we have medicines for the disease, the controlling of this disease won't be effective. And also these need very rigorous diagnosis, and also rigorous production of this diagnosis reports, and there will be so many processes that will be going on. So we need some kind of technology which actually automates and also make this process quick. So usually for these kind of diseases, we use reverse transcriptized PCR methods, which are actually expensive and time consuming as well as complicated. But those are the most accurate methods. But when we don't have that much of time, or when we have to do when we have a community spread as such, we have to look for other alternatives. So one such alternative is using diagnosing using X-rays. So both this tuberculosis and COVID-19 affect the lens. So how can we actually use this X-rays of the lens to predict this? So there will be some kind of granulosis that will be found, formations of granulosis that will be can find in the lens as when it comes to TB or COVID-19, that we can feed it to the model and train it, and and we can actually predict it. But here, what Deep Tech or Gently does is, they actually do this and also some other things. So why we actually go for X-ray is that it can assess the response to a treatment, not just how whether you have the presence of the disease, but it can also assess the response to a treatment, evaluate your disease progression, and predict the outcome, of course. So let's see what is the workflow. So the thing is that Deeptik AI has a set of mobile X-ray vans, and also there are many other endpoints or sources which can be diagnostic centers, hospitals, etc. And so and so. This X-ray vans actually collects this X-ray images And also, we also get these X-ray images from other diagnostic centers and hospitals, and they actually feed these images into Detect AI's cloud. So there is an AI algorithm running in the cloud which detects the abnormalities and generate the reports. So usually what happened when X-ray is produced, the radiologist has to view the X-ray, then uh, has to produce the report, which is very time consuming in the case of at the time of a pandemic when you have lakhs of patients, and also when we have limited number of radiologists, and going through each of these X-rays and producing a report is actually very tedious work. So what DeepTech does is that it actually produces a report on its own. So the doctors actually have the report in their hands. Now they just have to describe a treatment plan for the patient. So the thing is that the whole treatment procedure is getting quicker and faster, which can actually help in the control of the diseases. So here you can see that this lens is having some kind of granulosas here, which is in the highlighted area, than in this lens, which is actually normal. So there are some kind of challenges this detect or the Genki solution face, which they actually overcame. So what are the things? What was the challenges? The thing is, as I said, it actually detects these granulosas in the lungs. So there are people who have stents or pacemakers or kind of wires in their different parts of the body, not part of the body. So when we are taking the images, maybe our image data set doesn't have these kind of images with these kind of very kind of instruments installed inside the patient. So this can result in false positives. uh, so, uh, and also another so that is one challenge Genki faced earlier, and also, as I said, it's not just Genki's mobile X-ray vans that gives us the X-ray images, but also many other hospitals and diagnostic centers. And all of these X-ray machines are different kinds, which produces images of different qualities. Some have very high resolution images, while others are not that good. So we are having a lot of very kind of different images, and which results in a problem called domain shift, because we are using multiple sources as the image source. So what is a domain shift? So domain shift actually occurs when distribution of images used for training a model does not match distribution of the images that the model encounters when it is deployed in a particular situation. So here we have actually that situation, because when we are training the model, we are not expecting these kind of such variances. So how can Genki overcome these kind of challenges? So one method that they use to overcome this foreign material presence was that they use foreign material detector initially, so that which increases the sensitivity of the model when it encounters such kind of foreign materials, thus preventing false positive. Another thing is that they actually inserted a domain shift detector too, and also they actually deploy something called attention model. So attention model also increases the sensitivity of the model. So this is how Chetki overcome the challenges that they face. So this is another disease which is called diabetic retinopathy. So diabetic retinopathy is a very serious condition in people with diabetics. It is not that common, but uh, it is a very threatening disease when it comes, because as you can see, this is how a person with diabetic retinopathy sees the world, and this is it is like they will have black spots in the retina. So what happens is that when people with diabetes, they will have these ruptures in their nerve cells in the retina, which actually produces these kind of spots or black spots, which actually blurs their vision. So so there's this company called so there is this company which actually produces an AI product, whose name is Drishti. So it detects the presence of diabetic retinopathy during eye checkup screening process. So the main catch here is that this product is completely offline. That the algorithm is not running on the cloud. So you can actually take this device to any place, to any rural area, and actually do the checkup. This is the whole device. So this is so compact that you can actually take. And actually, this is not a separate device as such. The product that Drishti encompasses just this chip. So the thing is that the person can only identify that they have this DRs when this black spots appear. So that is such an aggravated point that they cannot actually treat this. Only this is actually asymptomatic. You don't have any other symptoms than these black dots. So only they will consult the doctor when this disease is advanced. So we have to actually detect this disease before it has advanced. So that is only possible if we integrate this chip which has this uh, AI algorithm into an eye checkup machine, so that whenever this person does an eye checkup during his life, whenever he's doing some kind of checkup, so this chip is actually employed inside this eye checkup machine, so that whenever he or she does this eye checkup, this algorithm also runs and does whether DR is also he is also diagnosed. It will also check whether this person has DR or not. So that is one advantage of this. That is, it detects the disease even before they have symptoms like black dots, which can actually saves the vision of so many people who have diabetes. So these are some kind of images that they use of the retina to train this Drishti model. So these are all retinas with DR. That is, these are not a normal retinas or retinas with any kind of infection, but these are retinas with DR. Okay, this is one of my favorite applications or one of my favorite healthcare products when it comes to AI applications, and the product name is Freenom. So this is for early cancer detection. We actually have so many cancer detection solutions when it comes to AI, but doesn't many of them are not for early cancer detection, or many of their applications are not that effective when it actually comes to the actual deployment of that product. Or many of them does what many of them does is usual and another version of usual biopsy, like they need actually pictures of the tissues, but here we call it a liquid biopsy, because here we are taking the blood samples and then examining the blood samples to for the early cancer detection. So we look for early signs of patterns in blood before the mutated cells or even the tumor appears. So it is very early detection that you won't have any mutated cell or even the tumor in your body, and it analyzes. We have this blood samples now. It analyzes the DNA, RNA, proteins, and other biomarkers which is circulated in the plasma of that blood sample, and this AI algorithm decodes the billions of patterns associated with body's response to specific tumor. It's like our body won't just start responding once the tumor is grown or the first mutated cell appears. Like the body starts responding much before that, even before the first mutated cell appears. So there are so many biomarkers which actually indicates this. So there are so many millions of patterns that you can actually identify to actually harness these patterns. So this is what Freenom does. They have something called multiomics platform. So it trains it with thousands of cancer positive blood samples, and it learns which biomarker patterns signify the type, stage, and treatment pathway of the cancer. That is the main catch, that it even actually predicts the treatment pathway. And also, it is also trained with negative blood samples, that is healthy blood samples, just to make the model learns that how a healthy blood sample looks like. Next, we have another application in the field of healthcare. It is not detecting of any kind of disease, but it is drug discovery, how we can discover drugs. So this is a platform where they do wet lab bio experiments and results are produced by ML models in the cloud. And this process is iterated or repeated. Uh, you can see the cycle here to come up with the best possible drug. So they actually, the main thing is that here they actually combines the wet lab and also the dry lab. So wet lab is the lab where the actual biological experiments happens, and the dry lab is where the computational or predicted experiments happen. So they actually combines them. Like we have a lot of solutions where the interdisciplinary research happens, but here it is like 50 or 1 is to 1. Like they both have the same they actually employs this wet and dry lab in equal importance, and that is how they actually produces the result. So they have actually a lot of products which are combined with an end-to-end life cycle of the whole complete drug design. So they have this rechem, which start with identifying the chemical compounds which can actually contribute to the drug formation. So this tool is to identify those. And then we go with rescreen, which actually which actually predicts how we can combine the first identified chemical compounds to in what ratios we can combine them and actually generate some kind of scientific and experiment variable relating to that. Then we move on to the next stage, that is rescreen run, which is actually a robotic automation hardware and software, which uh, which actually helps them to switch quickly between experiments. Therefore, we can actually run many experiments simultaneously based on this drug discovery. And also we have this rerun, which is nothing but it creates a mathematical signature for each of the biological condition that is tested, and that mathematical signature is called fingerprints. So then they create a representational learning model, which actually creates a high dimensional representation of our human cell images. Then they move on to reanalysis. So reanalysis is a tool which uses the previous tool, that is the rerun, and uses data science to compute the effectiveness of such drug compound. Then they actually uses repredict, which is a machine learning solution to model drug compound relation using the footprints, I mean the biological signatures that we have found earlier, and the chemical structure and the pharmacological properties. So this is a complete suite of how the whole drug discovery happens. Again, next is with ICH. So ICH is intracerebral hemorrhage. So intracerebral hemorrhage means it's actually a stroke that happens, a stroke of brain stroke, and which leads to bleeding in the brain. So which is a very intense condition. It's also a life-threatening stroke. So it actually happens when there is a lack of oxygen or supply to the blood to your brain, which can be the result of a head trauma or of hypertension or even uh, blockage of arteries to the areas where the blood supply to the brain is intended. So the treatment mainly focuses on stopping the blood and also removing the blood clot from the brain and also reviving the pressure in the brain. So it must be identified as quickly as possible because it is the brain, and if the brain is damaged, and it can actually result in the chain reaction and can also affect many other organs. So we have, if we have to make a decision and start the diagnosis, we have to do this as quickly as possible. And all the stakeholders or the doctors that has to be involved should also be informed as quickly as possible, because as we have so many stages involved, like as I said before, we have to stop the bleeding, remove the clot, retain the pressure, and also maybe due to the stroke some other organs of our body is also affected. So there are so many doctors in different domains associated when it comes to the treatment of the stroke. It is not just a doctor from neurology that will be involved. So we have so many stakeholders here. This tool is actually intended not for normal people like us. It's actually for doctors. Doctors actually uses it. So with IHS uses AI to automatically detect ICH stroke or non-contrast CT imaging in the doctor's network and alert on-call stroke team. Normally, things happen in a linear fashion when you go to a hospital with a patient who has stroke. So first, what they will do, they will do a CT scan, and they will pass the CT scan to the technologist for post processing, and next is moved to the radiology department for preliminary reading, and next to the ED clinical for examination, and then they refer to the neurologist, then the neurologist to the interventionist referrals, and then finally the treatment happens. So this is the linear fashion in which the treatment goes on. So this takes a lot of time, and by this time the condition of the patient may have aggravated, and finally he may need a ventilator. So to that extent it can aggravate. So what this product actually does is, after we have the CT scan, this tool actually predicts whether the person has this ICH or not. And instead of passing this whole report to this whole crew of doctors that I have said earlier, it actually send this report to the whole stakeholders, or the hubs, and we call it hubs and spokes. That is, in the spokes are the doctors in different departments, different hubs of the hospital. So if this document or this report is sent to this whole hubs and spokes, which will be involved in the treatment of this patient. So each doctor doesn't have to verify the report and pass on to the next level. Instead, this report is sent to all the doctors that will be involved. And after the report is sent, the next phase is the treatment. So the thing is that the patient doesn't have to remain in the hospital for so long, or even ventilator is something we don't have much, and also that is a resource that the hospital tries to save. So here, using this tool, you can actually save the ventilator, of course the treatment cost, and it's also reduced, and the stay time duration in the hospital is also reduced. So that is one tool that is used in the hospitals to actually treat the stroke patients. So these are some of the applications that are currently used. What I said before are currently used and deployed. So now let's see some interesting research papers that happened in this field. So there are a lot of research that happened recently in the area of COVID. So one such model is COVIDnet. So this, as I said before, here also they use X-ray images, because X-ray images is something we get data that is available is not easily, but available, and also that is one of the fastest diagnostic method that we can employ. So here also they use the X-rays for identifying whether the COVID is there or not. So the author proposed an open source model called COVIDnet, which uses projection, expansion, projection, design pattern, and being trained on COVID-X dataset. So the dataset that they use is called COVID-X. That is the name of that, which is also open source. So that is the architectural model of this whole thing. So there is considerable architectural diversity in COVIDNet architecture. It contains a heterogeneous mix of convolutional layers with diversity in the kernel size from 7 into 7 to 1 into 1, and different grouping configuration. It was pre-trained using ImageNet, and as I said earlier, then it was trained on the COVID set data set using the Adam optimizer, using a learning rate policy. Where learning rate decreases when learning stagnates for a period of time. That is called patience. That whole thing is called patience. So the term is patience. So this is the architecture of the model, that is the coordinate. This is the projection, expansion, projection design pattern. And also there is a lot of diversity, architectural diversity to increase the sensitivity of the model. So the next research paper is based on the automated screening of sickle cells using a smartphone-based microscope using deep learning. So sickle cell disease is a group of blood disorders which are actually inherited. And among them, one of the most common sickle cell diseases, sickle cell anemia. So when it comes to life-threatening diseases, this is some of the most common kind of diseases that you can see. So here, so in this, what happens in sickle cell anemia is that there are abnormalities in the carrying protein in the blood, which is called hemoglobin. So the whole solution is based on smartphone-based microscope. So the advantage is that it is very handy, and you can take this diagnostic tool to anywhere, even to rural areas, and actually does the diagnose can do the diagnosis. So this deep learning based frameworks which can perform this automatic screening of sickle cell using microscope in a smartphone, which have two networks actually, as you can see here. One is an enhancement network and another is a segmentation network. So first you have an image of the blood sample that is captured by the smartphone's microscope, and we have this enhancement network which standardizes the blood spheres captured by your smartphone's microscope spatially and spectrally, and it actually converts to an image which actually corresponds to a usual microscopic image of a blood sample. Then you have the segmentation network, which actually does the segmentation of the RBCs in the blood. So it actually segments the RBCs in the blood. And finally, you have a classification layer. So classification layer actually you have the segmented RBCs. So these RBCs, you have two kinds of RBCs. One is the sickle cell RBC and the normal. One is abnormal and one is the normal RBCs. So this classification layer actually classifies these RBCs and actually counts the number of sickle cell in your blood sample, and says whether you have sickle cell anemic or not. And another interesting paper is deep learning system for differential diagnosis of skin diseases. So skin diseases are very common. Almost like 1.9 billion people are affected with dermatology related diseases. But when we consider this huge number, the number of dermatologists that we have is very low, and most of these people just consult normal general health physicians when they have some kind of skin diseases. And the other thing is that all this kind of skin diseases have some kind of similar kind of symptoms, and unless you are that kind of experienced dermatologist, you cannot actually you cannot make a distinction between different classification of skin diseases. So now we have this deep learning solution. It's a research paper where we actually input the images of the skin condition. So this is one input, that is the images of the skin condition, and the second input is the metadata which contains all this information. So now we build a deep learning model using Inception V4, and we input the images and the metadata features. And this does a primary classification, which classifies it into 27 classes. Then it does a secondary classification, which classifies it into 419 classes. So one of the interesting outcome of this research is during the validation phase. So in the validation phase, the reference standards of the outcomes or the prediction were actually set by three boards of dermatologists containing uh, 35 dermatologists, and this DL model was not inferior to six of the dermatologists, and also it was even superior to six of the primary health practitioners. So it was also a promising kind of model. actually not even the general health physician actually can use this model to make to identify what the skin disease is. So the question is, why we cannot use AI in healthcare? Uh, the answer is very simple. Where human intelligence works better, don't bother to create an AI model or an AI algorithm. The thing is that there are places you can employ AI, and there are places we cannot deploy AI solutions. For example, in the field of psychology, you can actually employ AI for for actually taking for actually, there are phases where you actually interview the patients and does a lot of questionings and so and so stuff. Maybe AI can do that, but they cannot make sense of the data unless they have that they cannot make sense of the data. But a human intelligence can do that because we have something called empathy or sympathy and a lot of other emotional stuff. So not just when, comes in not just in the psychological field, even in the normal medicines, there are a lot of phases where we cannot employ AI. So when you look at during the early 90s or 2000s, the main actually intention of building an AI, like they were thinking of building an AI. So what is the use of this AI? So in 90s and early 2000s, the main intention was to build a treatment recommendation. That is, you actually say what the disease is, and the AI will give you the whole treatment pathway or the treatment recommendation. What's the medicine you should take? What are the tests you should take? All this, the whole thing. In short, they were trying to replace the doctors. Okay, so that actually doesn't work, and that is actually not even sensible because for that whole process, human intelligence is better because this kind of even diagnosing this disease, identifying what the disease is, and from scratch. Like if you know that the person is, for example, when we are identifying a person is having COVID, we actually know we are actually giving it an input like X-ray because we know it is something related which affects the lungs. So the subset is small. Here, the person is actually coming and saying his symptoms, and from nowhere, the AI has to, from a lot of huge set, the AI has to actually narrow it down to understand what the disease is and then recommend the treatment, which is actually challenging even for doctors with all the modern tools. So in that kind of situations, don't employ AI. So what can we use AI in healthcare? We can use AI in healthcare where the decision space is small. That is, decision space is small, like an yes or no. Or for example, as we saw the dermatology case, the decision space is small. There are certain number of classes on which the decision limits itself to, or whether this person has COVID, yes or no. That is a small decision space. Those kind of decision space. And also, even if there is a bad decision, there shouldn't be a large human penalty. We cannot afford to lose the life of a person just because our model didn't perform well. So in that kind of situation, like a life-threatening situation, we cannot employ AI. We can employ AI for like routine healthcare tasks. For example, when it comes to cancer treatment, the they usually take the slice of the tumors, and when as soon as the slice is taken, it has to be a process. In such a cases, because we have to make the process very quick, in such cases, you can use AI to process or understand what the slice tumor cells is all about, or taking inquiries from patients who are not in that critical situation, and providing app response using an AI algorithm, or identify individuals at high risk and provide extra services, like like our COVID cases. Like we actually identify a set of individuals who have this risk, and we are actually taking the X-rays and understanding whether these subset of people have granulosas in their lungs. So we are actually first identifying the high risk category, and then we are employing our tool for that. So basically, it is better to use AI to assist or add value instead of replacing someone. Okay. So let me tell you. story of IBM Watson to tell you, to make you understand what are the challenges that we face uh, in the field of AI in healthcare. So IBM is this huge company, and one fine day they decided to make an AI algorithm, or more like a bot called Watson. So they didn't create Watson for some specific purposes, but they created Watson as an experiment to just to know how well they can do in the field of AI. So what they did was that after creating Watson, they thought that they will market it or publicize it by putting Watson in a game show called Jeopardy. So Jeopardy is a game show in which there are three participants, and these three participants are given trivial questions. And these trivial questions can be like, who won this FIFA World Cup in that year? Uh, like so many kind of trivial questions. So the person has to press the buzzer, red buzzer. The person who presses the red buzzer first gets to answer the question, and if they answer it correctly, they will get points, and the person with the highest points wins the game naturally. So this was a game. Watson was actually introduced to this game show. So in order to do this, first they actually trained Watson in NLP, because they have to parse this question and then find the answer. So Watson was trained rigorously in NLP, and Watson won the game. Of course, yeah, kudos to the team. And after winning the game, people started asking, why can't Watson perform well in healthcare? Why can't we deploy Watson in healthcare? So IBM team said, yes, we can do that. So they suddenly started training this Watson with lots and lots of images of human muscles. So it was not one kind of muscle. They started training it with all kind of muscles, like leg muscles, elbow, arms, on a breast muscle, all kind of muscles in the human body. So they started feeding it with all scans, all kind of X-rays to the model. And the thing that you should remember is that Watson is something that was previously NLP trained, and now they are trying to train it with images. So I don't know who does that, but they did that. And Watson actually performed so badly during the validation phase. So the thing is that they didn't even do the validation or testing phase so well that they actually deployed Watson in many of the treatment centers, some of the treatment centers for the experimental purposes, and they tried to make treatment recommendation for cancer patient, and at places Watson were deployed started giving ad hoc result. That was actually very bad, and they actually took back Watson bots from them, from the deployed centers. So this is actually they actually they actually did all the things that I'm gonna discuss here. That is, they actually, first of one of the main challenges that we face is that selecting an appropriate use. As I said before, we cannot use AI to replace someone, but we can use AI in healthcare to assist or make our job easier, or kind of add value. Then we have to select appropriate training data set. When it comes to IBM Watson, they have a small data set, because the reason is that if it was one certain kind of muscle, it was okay. But it was like the whole muscles in the human body. And for if that is the case, you need such huge, big data set to train that. And they didn't have that, and you have to label them properly. That is, when it comes to IBM Watson, they labeled it using an automated tool. It was not manually labeled. And many of the images in the data set were fabricated. That is, it was not real images. And they didn't even do the testing properly. So all these are the things that we have to take care when we are actually deploying AI in healthcare. Yes, thank you. So that's it. When you are actually thinking of uh, going into AI in the healthcare field, these are some of the interesting facts that you should know.
Guys, like if you have any questions, you can ask Anushree now. Like it can either be about the session or AI in general, like how to like if you're even if you're a beginner and you want to pursue a career in AI, so like you can ask. Feel free to ask any questions to Anushree. Like yeah.
Ma'am, you have been present about technology to detect the sickle cell anemia. No? For that, the smartphone wanted the microscopic level camera. No, is it possible now?
It's actually a smartphone-like device. It is actually not a smartphone like the normal smartphone that we use. It's like a smartphone-like device which having a microscopic lens. So that this is actually a separate tool. So that the thing is that the main point is that we can actually take it's mobile and we can actually take this tool to even the remotest part. It is not a bulky tool.
Ma'am, can we use this? Actually, the AML is a branch of large data collection. No?
Yeah.
So, can we use this technology to in the field of spectrometry? By each of the elements or the compounds have their own spectral fingerprints, no?
Yes.
So, by using this, can we use it for identify different types of components and their isotopes?
Yes, actually, there are solutions in that, like using spectroscopy. We are using many, like even for one simple thing is that using the like I'm not talking about the isotopes. For example, in the one field that I have actually worked in is that waste segregation, the automatic segregation of waste. So in that, we have to first identify the material, segregate the waste according to the material, like whether it's a plastic, whether it's a paper, like that. So therefore, for that, we actually do the spectroscopy to understand what kind of material it is. Then we use statistical methods to model the variables to understand what kind of. We cannot actually build an ML model, but we have to use statistical analysis when we are employing spectroscopic methods.
Um, so we have a question from Sanju. Does all the applications you discussed fall under biomedical engineering?
Um, like not all of them falls under biomedical engineering. Like some of them are as I said, I don't remember what the product name is. Uh,
Watson.
yeah, Watson, and also there was some hard purely medical. I mean, wait, let me see. Yeah, not all of them fall under pure biomedical engineering. It is just that it can be employed in the healthcare field.
I hope that answers your question, Sanju. Yeah, cool. Guys, if anyone else has any more questions, like you can ask now.
I guess that's it.
Yeah, I guess I guess once again yeah, okay. Anushree, thanks a lot for being among us and sharing your law knowledge and like sharing your experience with us. Right now, lately, I have been also a little bit interested in implementing AI with healthcare. We have a mini project currently in this semester, and like that is revolving around the first parts you talked about, like using x-rays to detect the abnormalities. So all in all, I found this session really interesting, and like it would really help me, and I hope like all the participants who joined us today would feel the same. So all in all, it was a really great session, so thanks a lot for being among us.
Thank you for inviting me, and all the best for your mini project.
Yeah. thanks a lot, guys, for being. So I think that's a wrap, and like the whole session will also be like I'll be uploading the session on YouTube. So like for later, you can also view it. And if you have any doubts, like feel free to contact me, or like you can contact Anushree, like if that's okay with her. So
Yeah, yeah, it's perfectly fine with me.
okay, yeah,
Yeah, go ahead.
okay. Once again, Anushree, thanks a lot, and yeah.
Yeah, thank you.
Thank you, ma'am.
Thank you, ma'am.